Kinetic molecular model of an ideal gas. In this analysis, we take a microscopic view in order to relate microscopic properties to macroscopic properties in the ideal gas law. Consider an ideal gas of n identical particles, each of mass m. We drop the p subscript for convenience, so don't confuse this m with the total mass of the gas. We assume that the particles move with a range of velocities in various directions, such that the average velocity of the gas as a whole is zero. Each particle's kinetic energy is large enough that we may neglect the effect of gravity. The gas is enclosed in a rectangular container with volume V, which has rigid walls. The particles constantly collide with the walls in elastic collisions. The particles also constantly collide with each other and hence exchange energy and momentum. We are going to determine the pressure exerted by the gas on one wall. Let's look at the vertical wall on the right and consider one particle that collides with this wall. Let the coordinate system be x, y, z as shown. The particle has initial velocity v equals vx, vy, vz, and final velocity v prime, that is vx prime, vy prime, vz prime. During the short time that the particle is in contact with the wall, the forces exerted by one on the other are normal to the wall. So, since the wall is vertical, it is only the perpendicular velocity component Vx that changes, and Vy and Vz don't change, so Vy prime equals Vy and Vz prime equals Vz. Therefore, the analysis is reduced to a collision in one dimension. Although we know that, in general, the particle strikes the wall at an angle, we will consider a normal collision because we are only concerned with the normal component. From mechanics, we know that in an elastic collision in one dimension for a particle of mass m with initial velocity component Vx and a stationary wall of mass M, that the particle's x velocity after the collision is Vx prime is equal to m minus big M divided by m plus big M times Vx. Since the mass of the particle is very much less than the mass of the wall, m minus m tends to minus m, and m plus m tends to m, so we have Vx prime is equal to minus Vx. The wall has velocity components after the collision equal to 2 m divided by small m plus big M times Vx for the collision, which is equal to 0, since the mass of the particle is very much less than the mass of the wall. This repeats what we know for a collision between two masses of very different size. The collision exchanges momentum between the particle and the wall, with total momentum conserved. The particle receives an impulse that changes its x momentum by an amount delta px equals px prime minus px equals mvx prime minus mvx, which is equal to m times minus vx minus mvx, which is equal to minus mvx minus mvx, which is equal to minus 2mvx. This makes sense. The particle has Vx in the forward direction before the collision and is reflected with the same speed in the opposite direction, which conserves its kinetic energy, so its change in momentum is minus 2mvx. The wall experiences an equal and opposite impulse, and by momentum conservation, momentum 2mvx is transferred to the wall. Since delta px is equal to the average of the force in the x direction times delta t, we see that for this one collision, the average force in the x direction is equal to px divided by delta t. Thus, each particle exerts a force on the wall during a collision, and there are many particles colliding with the wall every second, so the force adds up and results in a pressure exerted on the wall due to the particles. The particles have a range of velocities and a range of Vx components. Out of all these particles, let's consider the subpopulation of those moving to the right with similar Vx. Not the same Vx, but in a narrow range dVx around Vx. If we take only those with exactly Vx, we will get few or no particles. In this analysis, when we say particles with x velocity Vx or with speed v, we mean that they are close to that value in a narrow range. Now let's see how many of these particles collide with the wall during a time interval dt. Since all of them move to the right at approximately Vx, they lie in a slab with the area A of the wall and of thickness Vx dt. We say that the slab is swept against the wall. The volume of the slab is A Vx dt, and the particle density in the gas for all particles, not just the subpopulation, is n divided by V, in particles per unit volume. Let F be the fraction of particles with speed Vx, which includes such particles moving to the right and to the left. The gas as a whole has zero average velocity, and we assume that velocities are distributed symmetrically amongst particles, so there are as many particles moving to the left as to the right, and hence a fraction half f of all particles move to the right. Therefore, the number of particles in the slab is this fraction times the number density times the volume. So f times a half times n over v times Vx dt times A. Each particle transfers momentum 2mvx to the wall, so the total momentum transferred to the wall due to these particles during time dt is dpx equals f times a half times n divided by v times A Vx dt times 2mvx. Hence, the force exerted on the wall by all these collisions is Fx equals dp dt equals F times n over v times A times m times Vx squared. There is no Fy or Fz, so the force F is equal to Fx. Knowing the force, we can find the pressure, but recall that we are only considering a subpopulation of particles with Vx. There are many other particles with other Vx that also exert force on the wall, so for now we can only calculate the partial pressure due to this subpopulation, which is Pf is equal to F divided by A, which is equal to the fraction F times n divided by V times m Vx squared. This is the partial pressure on the wall due to the fraction F of particles with speed Vx. To find the total pressure P, we average over all values of the speed Vx, which is equivalent to adding the partial pressures of all subpopulations with different speeds. We are going to relate P not to Vx squared, but to the total speed squared. Note that each particle has speed squared equals Vx squared plus Vy squared plus Vz squared. We denote the average by the subscript av. Now V squared av equals Vx squared av plus Vy squared av plus Vz squared av. These are average values over all particles in the box. Since the distribution of velocities is symmetrical, there is no reason why there should be more kinetic energy in one direction rather than another. So the kinetic energy in each of the three dimensions is equal. So we can write V squared average is equal to 3 times Vx squared average. And it follows that Vx squared average is equal to 1/3 times V squared average. Now the average Vx squared average is found by Vx squared average is equal to the sum of all speeds of f as a function of Vx times Vx squared, where f as a function of speed Vx is the fraction of the population at each speed Vx. We use this to find the total pressure P equals the sum over all fractions of Pf, which are the partial pressures for each subpopulation. This is equal to the sum over all speeds Vx times the fraction with that speed Vx times n over v times mvx squared, which is equal to n over v times m times Vx squared average. Multiplying by v, we get P in terms of the average speed, which is Pv is equal to 1/3 nm v squared average. The average kinetic energy of a particle is Kp average equals half m v squared average. So Pv equals 1/3 n times 2 divided by 2 mv squared average, which is equal to 2/3 n times a half mv squared average, which is equal to 2/3 n times Kp average. That's the average kinetic energy of a particle, which is equal to 2/3 kTr, where kTr is the total translational kinetic energy of the gas. Translational kinetic energy is due to translation, which is motion through space due to velocity. A monatomic gas consists of single atoms which only have translational kinetic energy. Returning to the derivation from PV equals 2/3 kTr, we obtain the ideal gas law if we set nRT equals 2/3 kTr, or kTr equals 3/2 nRT, since now PV equals nRT equals 2/3 kTr. For a monatomic ideal gas, the average particle kinetic energy, Kp average, is equal to kTr over n, which is equal to 3/2 nr divided by nt, which is equal to 3/2 nRT divided by nnAT, since the number of particles is equal to the number of moles times Avogadro's number. So the average of Kp is equal to 3/2 R upon Na times T, which is equal to 3/2 kBT, where Kb is Boltzmann's constant. This relates the temperature of an ideal gas to a clear physical quantity, which is the average kinetic energy per particle. An important measure of typical particle speed is the root mean square speed, or Vrms. Vrms is equal to the square root of v squared average, so that's the root of the mean of the square, which is equal to the square root of 3 kBt over m in terms of kb and particle mass, and square root of 3 RT over molar mass in terms of R and molar mass. Example 18.6 is a simple example with 3 calculations. First, find the average kinetic energy of a particle in an ideal gas at 27 degrees centigrade. Convert the temperature to Kelvin, and we have the average kinetic energy is 3/2 kBt, and putting in the numbers we get 6.21 times 10 to the minus 21 joules. Part B, find kTr, the total kinetic translational energy of 1 mole of this gas. So kTr equals 3/2 nRT, and plugging in the numbers we find it's 3,740 joules. Finally, part C, find Vrms of oxygen. The mass of an oxygen atom is 5.31 times 10 to the minus 26 kilograms, or 5.31 times 10 to the minus 23 grams, and the molar mass is 32 grams per mole, or 0.032 kilograms per mole. Vrms is square root of 3 kBt upon m, which is equal to 484 meters per second. That is 1,740 kilometers an hour, a very high speed. We can also find it out by taking the square root of 3 RT over the molar mass, which is also 484 meters per second.